We are looking at buffers, and this is section 15.1 through 15.3 in your text, or page 7 and 8 of the homework packet. And first, I'm just going to start out with a review of a weak acid problem. I have 1 molar HF. I got a Ka value. I know with a weak acid, HF is not going to break up to a large extent. So if the initial concentration is 1, the final concentration will be about 1, technically a touch less. And both the H plus and F minus will be the same or will be X. I can set my Ka value and ultimately solve for X or H plus, which is the square root of Ka times HF, and I get 0.027 molar or a pH of 1.57. Right, now what happens if I have add a common ion? We've talked about this common ion effect. And instead of just 1 molar HF, I also have 1 molar of, let's say, sodium fluoride. And what the F minus is going to use up some of the H plus and shift the equilibrium left, or products are going to combine to form reactants. This would cause H plus to decrease, making the pH increase. And notice it is 3.14 compared to the 1.57. How do we solve that? Well, with the H plus, I can say Ka equals H plus times F minus over HF, but I can manipulate that to solve for H plus, like I'm showing right here. And notice my HF and F minus, they're both 1. Technically, the F minus is a little bit bigger than 1, and the HF is a little smaller than 1. But that little bit bigger or smaller is insignificant. So it ultimately means H plus equals my Ka, which is 7.2 times 10 to the negative 4th. And I take the negative log of that and get the pH. There is something called the Henderson-Hasselbalch equation, and it says pH equals the pKa plus the log of the conjugate base over the conjugate acid. And if I look at this, what is the pKa? It's the negative log of Ka, which is 3.14, and then the log of 1 is 0, and it ends up being 3.14 plus 0, or 3.14. So either way, I think it's pretty short with this. Later on, we're going to learn that this Henderson-Hasselbalch will provide quite a bit of shortcut for problems. Here, they're both pretty short and pretty easy to do. What if I don't have the same amount of HF and F minus? It could still be a buffer. So a buffer, again, is a weak acid and its conjugate base. Okay, it doesn't have to be perfectly equal amounts, but it's a better buffer if it does. And let's take a look at this one right here. We don't have the same amounts. So it looks like we got 0.5 molar HF and 0.4 molar NaF. We have equal number of liters of each. So if I did a dilution factor and cut each one in half, the HF would go to 0.25, and the N and the F minus, we don't really care about the Na plus, it's a spectator, goes to 0.20. So if I look at that, I have, again, the X is going to be insignificant. So I have 0.25 here, 0.20 here, and the amount of H plus is going to change, but it's not going to be big compared to these other things. So I'm kind of taking that manipulated equation where H plus equals Ka times HF over F minus, and instead of plugging 1 and 1, I plug in 0.25 and 0.2, I get a molarity and I get a pH. Notice because I have a little bit more acid than conjugate base, the pH is a little bit less than the 3.14 I had before. Doing the Henderson-Hasselbalch, again, pH equals the pKa, which is 3.14, the log of negative 0.20 over 0.25, and that's a minus 0.10. So subtracting, I get pH of 3.04. Okay, I'm going to keep going, and I have a buffered weak acid where I add strong base. And I think in this one, we're going to see where the Henderson-Hasselbalch equation is really going to help us out. So let's say I actually take that last problem and I convert liters times moles per liter to figure out how many moles I have of both the HF and NaF. Okay, and then I know I add 0.03 moles of NaOH. So what's going to happen is that OH is going to convert HF to F minus. I think I wrote something about that. The added OH converts HF to F minus. HF plus OH minus makes H2O plus F minus. And that will work out and not affect the pH much as long as you don't exceed the buffering capacity. Notice the moles I added is much less than the moles of what I have originally. So that shouldn't change the pH too much. So the 0.25, I subtract 0.03 from that because the HF got converted to NaF, and that becomes 0.22. And I add 0.03 to the 0.20, and that becomes 0.23 because I converted HF to NaF of 0.03 there. So now I punch that into the Henderson-Hasselbalch, and here's the beauty of this. Okay, if you're using Ka values, you got to go back from your moles and convert to molarity. But with Henderson-Hasselbalch, you can either do it in moles or molarity, kind of like an icebox in that way. So I can just say pH equals the pKa, which is 3.14 plus the log of the base over the acid. Now the base is slightly bigger than the acid, so it ends up being plus 0.02, and it ends up being 3.16 instead of the 3.14 I had when I had equal amounts. Okay, what if I add acid to this? Same problem. How is that going to work? And it's going to work pretty similar. I'm going to take my 0.25 and the 0.25, I add 0.03 moles, okay, assuming it's not affecting the volume. And this time, it's going to cause what H plus is going to cause F minus convert to H plus. So HF is going to get bigger by 0.03, going from 0.25 to 0.28, and the NaF is going to get smaller by 0.03, going down to 0.17. Okay, and again, a lot easier using Henderson-Hasselbalch. pH equals 3.14 plus the log of the base over the acid, and notice I have more acid than base, so I get this minus 0.22. It lowers the pH because I have more acid than base, which makes sense, and it's 2.92. So just looking at this, notice by adding the acid, I think I was originally at 3.04. By adding acid, I dropped to 2.92. It's not much of a drop, but it is a drop. And I lost everything here. When I added base, I went from the 3.04 in that expression to, I don't know if I'm going to find this, 3.04. That went up to 3.16. So when it went, what, up 0.12 and when it went down 1.12. So you can kind of see how those amounts kind of stay consistent to in which way they're maneuvering around. Okay, that is a weak acid, or yeah, that is a buffer solution with a weak acid and its conjugate base. And I think that's it for this video. Thank you.